Good morning everyone. Today we will be studying about asymmetric synthesis. So in asymmetric synthesis, first of all we have to understand what is asymmetric synthesis. There are various names that can be used for asymmetric synthesis. It can be called as chiral synthesis or selective synthesis. It's nothing but a form of chemical synthesis in which an achiral unit, which is ensemble of substance molecule, is converted into a chiral unit in such a manner that unequal amount of stereoisomers are produced. Okay, so generally when there is no stereoselectivity or there is no preferable formation of any one particular enantiomer or diastereomer, in that case equal amount of enantiomer or diastereomers are formed. For example, if we do the reduction of this molecule using NaBH4, we'll get this OH and methyl group plus another isomer where OH is away from the weaver. So this carbon is a chiral carbon. Okay. Because it has 4 different substituents, hydrogen is not shown here, but it is present. So that way these two will have different isomers. Now this synthesis is not a chiral synthesis. It's not a asymmetric synthesis. In this type of synthesis, the ratio of both the products is 50-50%. Okay, if you see the rotation here, it is S and this one is R. Okay, but so this is example of racemic reaction, but taking the same substrate and a chiral reagent, something which is chiral. Okay, and we proceed with this reaction. In that case, what happens? A preferable enantiomer will be formed. Both the same products will be formed as we have seen in the Bohr reaction, but the ratio will be different. The S enantiomer will be formed in much more amount as compared to the R1. So if this kind of reaction takes place, this kind of products we obtain, then we call the synthesis as asymmetric synthesis. So if we have to write down the definition, we can say asymmetric synthesis is defined as a reaction in which an achiral unit in an ensemble of substance of substrate molecule is converted into a chiral unit in such a way, in such a manner that unequal amounts of stereo isomers are produced. Okay, so this will be the definition, and if you write it in simplified form, we can say it is the synthesis of a compound by a method that favors the formation of chiral molecules in unequal amounts. Okay. Now, two terms come with the asymmetric synthesis. One is stereoselective. So, asymmetric syntheses are often called stereoselective. And stereoselective is if one product is formed exclusively. That means if there is a possibility of formation of two enantiomers in any particular reaction, but only one enantiomer is formed in the product, those kind of reactions are stereoselective. Okay, so we can say asymmetric synthesis, often called stereoselective. If one of the product is formed exclusively. By exclusively, that means the second product is not obtained at all. Then the reaction is called stereospecific. So again, if we discuss these two terms, stereoselective term is used when one chiral molecule or one enantiomer or diastereomer is formed in excess and the other one is formed in the very small amount. And stereospecific term is used when only one particular enantiomer or diastereomer is formed. Now, if we have to define a stereoselective reaction, we can say that a reaction in which one of a set of stereoisomer is formed predominantly, then the reaction can be called as stereoselective reaction. We can further specialize them as diastereoselective or enantioselective. That depends upon whether it is a diastereomer or an enantiomer that is being produced selectively. Okay, so let's take an example. If we react A and B and product C and D are formed, and if these C and D are stereoisomers, then there is a possibility of reaction being stereo selective if C and D are formed in unequal amounts. Okay, if C and D are formed in unequal amount, then the reaction is stereo selective. Now we can further specialize them as diastereo selective or enantiomer selective. That how we specify. If C and D are diastereomers, then it is diastereo selective. If C and D are enantiomer, then it is enantiomer selective reaction. Now, if we have to define the stereospecific reactions, then these are reaction in which the stereochemistry of reactant completely determines the stereochemistry of the product without any other option. Or in simplified word, we can say a reaction in which only a specific isomer reacts to give one and only specific stereoisomer. Then it is called stereospecific reaction. For example, let's take these cis and trans 2 butenes. Both of these are reacting to the same substrate under same conditions, and we are obtaining tricyclic substituted product. In case of cis, the product is also obtained as cis. In case of trans, the product is again trans. There is not a possibility that you react the cis isomer and you obtain both cis and trans in the product. There is only one option. Cis will give you cis, trans will give you trans as a product. So if the reaction is of this type, then we call them as stereospecific reaction. Okay, next thing is optical purity or enantiomeric excess. Whenever you have a asymmetric synthesis, that means one of the enantiomer will be formed in excess over the other always. So you will have to check the optical purity, how pure is your product, how much amount of one enantiomer is there. Okay, so that is measured by enantiomeric excess. Enantiomeric excess is defined as the excess of one enantiomer over the other generated in an enantioselective reaction and is usually expressed as the percentage of the whole. Okay, what it gives, it is used to measure the efficiency of an enantioselective reaction, like how efficient is that particular reaction is. So there is a formula for that, optical purity or percentage enantiomeric excess. It is given by percentage enantiomer formed, which is in excess, minus percentage of enantiomer formed, which is in less quantity. Okay, so that can be expressed in the term of optical rotation. Optical rotation of the mixture divided by optical rotation shown by your pure substance into 100. So this is the formula for optical purity. And if you have to find out the enantiomeric excess in terms, if you have the concentration of your both the enantiomers, then you can use the formula like this: 100 into difference of the concentration of isomer. Let's say R isomer is in excess, then the concentration of R minus S will give you the difference in the concentration of both the isomers divided by total concentration of both the isomers combined. So this way you can find out the percentage of enantiomer which is in excess. Now since this gives us the purity of the mixture we obtained, so let's see how it shows. If we have 50% of both enantiomers, then using this formula we can do 100 minus 50 minus 50 into 50 plus 50. Okay, so this will give us 0. So 0% enantiomeric excess. None of the enantiomer is in excess. If you have 75-25, then it will be 75 minus 25 divided by 75 plus 25. So this 100 will cancel out and you will get 50% enantiomeric excess. So that ways you can find out how much excess one enantiomer is over the other. This is for enantiomer. Similarly, you can find out the optical purity of diastereomers also. Okay, the formula will be similar. It will be something like percentage diastereomeric excess is equal to 100 into your concentration of major diastereomer minus minor diastereomer divided by sum of both major plus minor. Okay, so this will give you the percentage diastereomeric excess. Now for asymmetric synthesis, there are two ways. One is chiral pull synthesis, another is chiral auxiliary approach. So what happens in the chiral pull synthesis? Enantiomerically pure molecules which are available in nature are used to synthesize a new molecule. And since the starting material is already chiral, so an approach is used in such a way that you will get only one particular enantiomer or diastereomer in the product from using that starting material. Okay, so this is the oldest and simplest way of synthesizing any enantioselective product. Okay, if we have to synthesize some particular enantiomer from a chiral substance, we will have to perform the reaction in such a way that only single product formation is possible. So that kind of product might be obtained using SN2 reaction. SN2 reaction is a single step reaction and it occurs with the inversion of configuration. So let's say if your starting material or your reagent is having R configuration, then the product obtained will be S. So that ways your configuration changes. Okay, so what they do, they take the starting material, a chiral substance, and react it with a nucleophile. Transition state occurs. This kind of transition state occurs in the SN2 reaction in which simultaneously a bond is being formed and a bond is being cleaved. So the bonding of nucleophile will be only possible from the opposite side to that of the leaving group. Only possible product formed is this one. Okay, so the basic concept behind this chiral pull synthesis is they derive the starting material from the nature. Some chiral substance like amino acid or any other chiral carboxylic acid or monosaccharide they derive from nature. They perform a reaction, SN2 kind of reaction, and obtain the desired product. Now the best part about this reaction is the functional groups that act as leaving group. These groups are generally poor leaving groups. If you could remember from your SN1, SN2 reaction mechanisms, poor leaving group favors SN2 reaction. So that's why these kind of groups, when present in any starting material, they facilitate the SN2 mechanism and in turn our desired inversion in configuration. And since there is inversion in configuration, only single product will be obtained out of the two enantiomer. Only one enantiomer will be obtained. Okay. After that comes the chiral auxiliary approach. In chiral auxiliary approach, what they do, they take a prochiral substance, or you can say a achiral substance. Prochiral substance is something which have a possibility of forming a chiral substance on replacement of the one group attached to it. Okay, let's see it with an example. For chiral auxiliary approach, what we do, for chiral auxiliary approach, we used a organic compound which is chiral, or you can say which is optically active, and we club it with the starting material that is not a chiral substance, and then we perform a reaction which undergoes enantioselective. Then what happens? Then the auxiliary chiral compound that we attached is removed from the product form, and we obtained a optically active compound which is enantioselective. Okay, so what happens? We temporarily incorporate the chiral auxiliary molecule in our achiral substrate and then guide the selective formation of one of the enantiomers and then remove the chiral auxiliary substance. So I have written down the examples of chiral auxiliary compounds. This is 1s2s pseudo ephenamine, and the other analog is 1r2r pseudo ephenamine. So these two molecules can be used as chiral auxiliary compounds, and I have given a general process of chiral auxiliary approach. So let's see, this is our prochiral substance. Prochiral substance means any substance which have a tendency to be converted into a chiral substance on replacement of one of its hydrogen by a group other than the already attached functional groups. Okay, so this is our prochiral substance. We attached a chiral auxiliary, that is HXC, with this molecule. OH is replaced by XC. Now it's a chiral molecule. Now it becomes chiral substance, and distereoselective reaction is performed. Of course, since it's a chiral compound, one particular diastereomer will be formed. Now the chiral auxiliary substance that was attached was removed again, and again the XC is replaced by OH and the desired product is formed. Okay, now what happens? Basically, the chiral auxiliaries are optically active compounds and they facilitate the introduction of chilarity in otherwise achiral starting material. What they do? The substance is achiral. They will introduce the chirality using chiral auxiliary substance and then perform the stereoselective transformation, any reaction which will give you distereoselective product. Then again that auxiliary group is removed and the desired product is obtained. This is the basics of chiral auxiliary approach.